So this continues, starting with problem number 13, the second video on the solutions for test number 6 in the fall 2013 AP Physics exam. In this particular problem, number 13, I'm asking you to demonstrate that you have an understanding not only of Newton's laws, but in particular how to handle a pulley. So the first thing it asks you to do is to draw me a free body diagram for each block. So we start by isolating the two blocks. So there's the first block and there's the second block. Then we inventory the forces. Each one has a weight. So that'll be weight 1. This will be weight 2, and you need subscripts because they have different values for the weight. They have a normal force. This has a normal force going up. That'd be N1. This has a normal force going perpendicular to its surface. That's N2. Tension. There is tension. There is this rope here. This rope is pulling this away. Call that T. Now, if this pulley had mass, we'd have to draw a free body of that pulley, and that pulley would be seen as the one pulling this block. But this is a physics pulley. It's massless, frictionless, and right now, until we deal with rotation, we can't handle a pulley that has mass. We'll come back and make this more realistic later in the course. So, all the pulley is doing in this type of pulley is to rotate the direction of this force to a new direction over here. Another way of looking at it is to rotate our coordinate system down to here. So who's pulling on the block 1? Well, it's block 2. So this one's pulling away from the block. Likewise, ropes can't push. They can only pull. So those tensions got to be going away from that block. And it has to have the same magnitude as over here. It has to be T. No subscripts. Say T1 and T2, we're trying to apply the third law. They have to have equal magnitude. We'll come back and show that they're in fact equal and opposite directed, as well as equal magnitude. All right, now, what about friction? This thing, we're doing no friction in this particular exam, so it's frictionless. So weight applied, normal tension, friction. You got to want the force, apply 1F if you want to solve a problem. Now, you can apply one axis anywhere you want. I'm going to put my axis, I guess, in green. So here's my axis here, like this. And I often like to put it on my picture up here. Now, here's the thing. This X is going along this rope. That X needs to now continue to go along this rope, because when this block moves, that block moves. So this pulley rotates your axis. This axis X is now in this direction. And that means the Y also get rotated. I call this the rule of the gun, something I picked up when I was at West Point. So this axis here should look like this. There's X, there's Y. It is essential that you connect the motion of one block to the motion of the other. Now you can do this through constituent equations, that is equations you substitute and put in subscripts and acceleration, but the easiest way is to do this way of rotating the axis, called the rule of the gun. Now, this angle here, which I'll now make red, this angle here is needed because this axis lies on Y, this axis lies on X, but this weight does not lie on either one. So we're going to need an angle theta, which is the angle of this incline here, right there, in order to break that vector into its X and Y components. If you've done all of those things, then you've drawn a proper free body diagram, and we can now use that and read that to solve Newton's laws. So in the next part of the problem, find the acceleration of the second mass, M2, in terms of M1, M2, G, and theta. In fact, because they're connected by a physics string, both blocks have the same acceleration. So all they're asking me to do is to solve for A. From this free body diagram, I have the sum of the forces in X is equal to the mass of this block, M1, times AX, And for this one over here, the sum of the forces in X is got to be the mass of that block, m2ax. That's just Newton's law. Now I need to write by reading the left-hand side from the free body diagram. How much of this is along X? None of the normals along X. How much of the weight's along X? None of it. How much of the tension? All of it. So it's a T, and it's in the positive X direction, so it gets a plus. That's m1ax. I'll call that equation 1. Over here, how much of n lies along X? None of it. How much of T? All of it. Which direction? Negative direction. Minus T. Notice how I ended up with this T in the positive X and this T in the opposite direction by the third law. If block 2 applies a force, a tension force of magnitude T, then block 1 must apply a tension force on block 2 that's of magnitude T, no subscripts, in the opposite direction, in the minus X direction. Our third law has been fixed by our rotating around the coordinate system. Then I have this W. This W has a component along X. It's this side of the triangle, which is the opposite side. So I have W. O is closer to S, so I use the sine function. And it's pointing, if you want to get to W, you walk down here, you got to go in the positive X direction. So let's get the plus sign. That's equation 2. Now the fastest way to solve for one of these problems for A is to add the two equations together, because by the third law, one of these positive T's, which is an interaction force between the two objects, is going to be canceled by the opposite reaction force, the minus T. So add 1 plus 2. T minus T is 0 plus W sine theta. M1ax plus M2ax, I can factor the ax out, and I get M1 plus M2ax. Solving for ax. Ax is equal to, oh, I left off when I did this W, this should have been weight 2. Be careful. Need my subscripts because it came from this diagram. So that would be mass 2 times G times the sine of the angle divided by M1 plus M2. I'll rewrite it, make it a little clearer. Notice the mass is canceled, so that's unitless. The sine of an angle is unitless. G is an acceleration. The left-hand side is an acceleration. If this thing was at 0 degree incline, then the sine of 0 would be 0. The object wouldn't accelerate. If this object had an angle of 90 degrees, if you were just dropping that block straight down, this would be 1, and you would get M2 divided by M1 plus M2. All right, that should have solved that part of the problem for number 13. Number 14. Number 14 is a problem involving reference frames in relative motion. So in problem 14, you've got a boat here, and the boat is going to drive this away as seen if it was in stationary water, but there's a water current driving it this away. So its motion is going to be like this, as seen from the shore. So we need to have some things. We are being asked to need the velocity of the boat relative to shore. If I knew that, then I could determine the position of the boat relative to shore, which is what the problem asks. It says a boat can handle 2.6 meters per second in still water. Okay, that is the boat velocity of the boat with respect to the water. So VBW 2.60 meters per second, and according to that axis in the j-hat direction. If the boat points its prow directly across the stream, whose current is 1.1 meters per second, that is the velocity of the water measured with respect to the shore. And the stream is flowing this way, so that's the way the water's going. So that's equal to a minus 1.10 meters per second I-hat. And it says, what will be the position of the boat relative to its point of origin after 3 seconds? If I knew the velocity of the boat, I can multiply its velocity by 3 seconds and find its position vector, because it's not accelerating. All right? So that's what I need. I know that R is equal to the velocity of the boat with respect to the shore times time. That will give me the position of the boat as seen by the shore. My problem is to first find this. Well, it turns out that's relatively easy. In fact, they've almost given it to me. They say to find that, I need to do vector addition of these two vectors. This is just a Galilean transformation problem, and it was in the book, and similar to the one with the Huck Finn problem in the homework. So, finishing it out, VBS is equal to the velocity of the boat with respect to the water plus the velocity of the water with respect to the shore. This is equal to minus 1.10 meters per second I-hat, that was this one, plus 2.60 meters per second j-hat. That's this velocity here, or this one. I put them in the opposite order that I wrote them here because I wanted to put I, the x component, followed by the y component. It doesn't say in anywhere that I have to convert this and find the magnitude or an angle. It can leave it in Cartesian. So now RBS is equal to 3 seconds times minus 1.10 meters per second I-hat plus 2.60 meters per second j-hat. So the position vector as seen by the shore will be minus 3.30 meters I-hat, and 3 times 2.60 will give me 7.80 meters j-hat. Again, they don't ask you how far away the boat is. If they ask you how far, then they'd be asking you to find the hypotenuse of this. And you draw the triangle and use the Pythagorean theorem. But they didn't ask that question in this particular problem. Alright, that finishes this video. In the third video, I will do the bonus problem.